We're streaming, baby. Welcome to Linear Algebra Done Right. Let me clean up my environment from what I was working on yesterday. Let's see here. LADR, source, fields. We'll open that up. There we go. Now, this isn't going to work because I changed the setting. Oh, it did work. That's weird. Now it wants me to install a more recent version of Cock. Why would it want that? I thought this wouldn't work because I didn't have a project file. Hey, Gerhard, good to see you again. Thanks for coming back. Let's see. What are we doing today? Let me make sure the book is opened up. I gotta go into Finder and downloads LADR PDF. And we're going to plop it right next to Emacs. There you go. So last time we were going to define addition, and we got stuck. Zipwith worked, by the way. Just had to add a few underscores in places. So I'm going to talk about that. So there's a few things to talk about before we get started here. How do we like the field for the theme for the day? Is this a good theme, or should I explore different themes? It's really dark. It has some nice red and yellow here, and I like it. I think it's a good theme for the day. I'll be satisfied if that's our theme for the rest of the day. If I'm feeling it, I might go past 5 today. Oh, increased font size. Thanks for reminding me. I always forget that. That's one notch bigger than it has to be, I think. I don't know. Is this fine? At this level? All right. Started almost 5 minutes early, but that's why I'm taking my time to get started. One higher. All right. That's all good. So where is addition in the book? I mean, I don't really need it to be in the book. Oh well. Addition. There it is. This is where we got stuck. But we got stuck. So here's the thing: is we're doing vector spaces, right? So ultimately, let me go down here. Here's what I figured out. So what happened was after stream was I talked to some friends. I didn't mean to work on this off stream, but I was just like having conversations, and what some people recommended was require import vector.fin. I think it's vector.fin. Why did that break? Oh, because I put the definition of scalar mul above my instance declaration. I am Woe. Thanks for the follow. I don't have a follow animation. I don't understand. I don't have that good Twitch stuff, but I am Woe. Really appreciate the follow. So vector.fin is it vectors.fin? It's vectors.fin. And if we do check fin 4, maybe it's fin? Not interested in follow animations, but thanks for using Emacs. Yep, it's all about Emacs. This is Doom Emacs. This is the Doom build. So ultimately what we can do is cock standard library. Fin. What is fin? It makes it okay, why is fin n not fin n should be working? Oh no, it's gonna every time I do definition. It's not too. It should be fin n. Fin n is a way of expressing an interval, right? So like in math notation, we do 0 dot dot 4 to mean the interval 0, 1, 2, 3, 4. And I forget if it's exclusive or inclusive, but fin is not found in the current environment, which is weird because I imported vectors.fin. Maybe it's up here. Okay, this isn't working. So we're gonna the overarching point though. The overarching point though is we're not here for like one particular instance of vector space. So we're gonna make a vector space class. Ultimately, it's gonna be like this, and an instance of that class is gonna be, you know, R4. R has type. What is going on here? Let me make my response bigger. Oh. No, you do the type. Oh, it's just T4. Open some scope. Yeah, I should open. I'm in RScope right now. But I'm gonna have to look up. I'm gonna have to look up documentation for like open scope because I don't have it memorized. I meant for fin. I think because I imported vector fin, T is actually fin. So up here, T is type into nat into type. That's the vectors we were working with last week. But here, this is just the nat into set. So basically, definition R4. We'll do T4, but we can't give it a type. And if I say, I think I can look like this. Definition X's is of type R4. I think it looks like this. Fun n into match and width 0, and then this is just the data. So let's just have a vector of all 9s. 1, 9. And let's just say, well, there's an easier way to make a vector of all 9s, of course. It's underscore into 9. And then, does that not work? The type of this term is a product, while it's expected to be of type R4. Here was my understanding, based on the discussions I had with my friends, is that fin this fin business allows you to make vectors that are finite dimensional because they terminate at the argument into the type. So it's still an index type that can create finite dimensional vectors, but it does it by making them functions from nat. Well, not nat, from fin n. So fin n is, but this doesn't look like the definition of that. Open some scope for fin. Yeah, I should open some scope for fin. Hey, Deflate, how's it going? Good to see you. Thanks for coming to the stream. We're just getting started here. I'm a little confused myself, so maybe we should just get back to this zip width project and worry about this later. Because I said we would start by oh, someone remind me to push to GitHub tonight. Matt, great. I'm glad you came. I was figuring out the fin thing you were telling me about. And figuring it out in Cox, so... But we'll get back to that. Right now, I'm going to finish zip width plus. Why is this taking so long to execute? It's taking forever. Something's happening. Patience, patience. We are... Ryan Allred, thanks for the follow. Good to see you. Thanks for coming in today. All right, we're waiting for this thing to execute, and it's totally not happening. So I'm just going to kill... All right, it finally happened. There you go. All right, so we need to figure out this zip width business. So a friend told me that you can actually implement zip with, oops, clicked the wrong thing. You can actually, I want this over here. You can actually implement zip with rect2. What is rect2? It's a variation on rect1. What is vector rect? It is, I think I need to go here into def. So rect is trect. Rect is an induction principle that lands in for things that land in type instead of prop. That's basically all it is. If it's ever going to work. For some reason, my cock run time is really slow. I might. It's not usually this slow. It's not usually this slow. Something fishy's going on. But my friend told me there was an implementation of zip with rect2, and he showed me it. But what I need to do is check rect2. But I can't check anything because as soon as I go to stop the runtime, it works. All right, there you go. So rect2 is this complicated thing, but it can implement zip, I'm told. And trect... Oh, this is terrible. It's really acting funny today. So trect, let's read this. Let's get into this. It's for every type, and for every nat, there is a tan into type. So it's a function from the vector type into type, right? If that function holds, of 0 and nil, then it holds of the n plus 1 case. Well, I mean, sorry, I screwed that up. If it holds of 0 and it is one thing, and the other thing is if you prove that it holding of n implies that it holds of n plus 1, you get it landing for all n. And you do this with landing into type instead of into prop. So induction principle is the exact same thing, but it lands in prop instead of type. You see that the P lands in prop. So rect2 is a variation on rect, and it has this totally bad news signature. So if we have rect2, we have implicit types. We're just going to I want to try a zip implementation with this because I was told it works. I was shown that it works, but I'm not going to look up that solution because that would be cheating. Check rect2 for all n in n tan arrow tbn arrow type. P0 nil A nil B. So this is for for two different types. So if I it's not a notation, I think argument. No, that doesn't work. Here, I'm just going to require import reals. And what we're going to do is we're going to pass in. Oh, hold on. This is not going well. This is not going well at all. This might be too complicated. I might just go back to functional programming as I know it. If I know it. If I know anything, for goodness sakes. All right, Gerhard said that it works. So we're gonna go back, fixed point zip, AB type, and nat. We're going back here. Deflate if you want to pipe in about getting us using fin here. Just let me know. It might. But I gotta focus on one thing at a time. I can't go all over the place. So this is. Let's make it like this. Fun. Why bother with zip instead of just going straight to zip with? So I have a more complete utility library. All we care about is zip with plus. I know. But I want a more complete utility library. So this is the function zip. Zip equals zip with comma. Does that actually work? Does that work in Haskell? Zip equals zip with comma? I've never heard of that. I've always done it the other way. Because comma is like a piece of syntax. It's not. Oh, well, that's interesting. Um, Fixed point zip is defined as fun x's, fun y's into match x's in t underscore m return tbm arrow t a times bm with, let's try this, nil underscore lands in. This is really convoluted, but it's convoluted for a necessary reason. So if you're watching the stream and you're like, what the heck is going on? Last Sunday, we tried the naive implementation of zip, and it totally didn't work. X is prime. Huh. Yeah, that's fascinating. That is fascinating. So we found this pattern. All right, Gerhard, you're up because this is going to fail, and I'm going to ask you what you did to make it succeed. I can't. I need an n prime here because. All right, let's paste in the zip width that worked because I don't want to get bogged down. I actually want to like read some of the book today. So let's paste in the zip width that worked, and let's see what happens. All right. All right, here we go. We got the type signature for zip width. If anybody like hasn't seen, so this is like intro functional programming. This is the first few chapters of any functional programming book, right? So if you haven't seen zip and zip width, just let me know and we can take an aside and like I'll explain them. But we're trying to implement them in Coq, and it's just like totally not working. Okay. So I really want to understand why this never worked. Oh my god. You're kidding me. Why is that different from what I did? Oh, that's terrible. I'm so upset about that. This looks exactly the same as what I did. I feel like we were so close. We were like an inch away last time, Gerhard. All right, so we have zip width. So let's get back to business. I wanna do this casing for zip width just because for some reason I don't think I want to do camel case for this library. So why is this different? Let's inspect this to see what's really going on. No clause for cons. See, I tried this and it didn't let me do it. Oh, but you're saying put underscores in the return. You're saying put underscores in the return, which is fine. Which I should have. It didn't occur to me. I wasn't innovative enough. Yeah, you know what? You put underscores in the return. Okay, thank you so much, Gerhard. I didn't know you could put underscores in the return. Yeah, it's okay if you didn't get it to me like right then because I'm trying to only work on this on like Sundays on stream, you know. So we got fixed point zip width, and let's try definition zip. This isn't going to work with Cox syntax. I don't even need to type it right. Zip width, but this should work. Fun A into fun B into A comma B because you know tuple comma and everything is cannot infer the implicit parameter. Okay, I need implicit. How do I do that? Can I do that with definition? N is in that. Oh, use pair for constructor. Yeah, that's pretty nice. Instead of fun. Oh, just zip with pair. A legal application of non-functional construction. Oh well, I might as well just do ABC type and nat. ABCN, and let's see what this does. Oh no, I forgot. I need to put pair here. See, how am I giving it? Oh, I need to do at zip width, ABCN pair. Pair has type A arrow B into H star B. I was expected to have type. Oh, I don't give it a C. There you go. Yep. All right, we have zip and zip width, baby. We're functional programming. Good stuff. So the whole fin of n interpretation. Let me see. Okay, here's the thing. Let me see if I get to the vector type class today, and then we'll talk about different instances of vector type class. So I need to open up a term. Okay, it's the right cock top. I need to do. Oh, I'm in the wrong projects. Someone remind me to go to Git. I don't know if we're doing GitHub or GitLab, but coxy utils. I think that's all it needed. So I should be able to import utils now. I'm just not going to try to like require import utils. It worked. So after I have all of my instance declarations. So if you weren't here last week, we made a ring type class and we made a field type class, which is like the basic algebra that's like underlies vector space. And we declared instances. So if you don't know about type classes and instances, just let me know. We can talk about it. But let's keep moving. Okay, definition. What should I just call it? Addition. A is a type. A is a field. Now, if you look closely at scalar mult, you might find that I can make it work. Yeah, I can make it work with ring, but I'm just sticking closer to the book. X's, Y's are of type TRN. Zip with fun X into fun Y. No. I can just say RAD. Zip with RAD X's, Y's. And it works. We have addition. Simple as that. So we're writing our first proof, everybody, because what's next in the book? It is commutativity of addition. So we're finally writing a proof. Theorem. Addition. Commute. Maybe should I just abbreviate it like that? I think that should be fine if I abbreviate it like that. But I want to do it over every type class. Hold on. How can I recycle theorems and lemmas between instances? Not type class instances. Or do I have to prove them? No, you know what? I'm going to have to prove for each instance. There's going to have to be a proof for each instance because this theorem is going to be an argument to the instance declaration. Now, what I haven't seen yet is instance declarations in theorems. All right, so we haven't seen instance declarations in theorems. So let's see how it goes. A is a type. I'm like forgetting if I can do implicit in theorems. Field A and nat. For all, here, I'm going to do it like this. X's, Y's, T, A, N. Addition X's, Y's equals addition Y's, X's. Oh, it's not going to be, like that. It's going to be like this. It's going to be like this, yeah. So, unfortunately, we're going to have to prove these theorems once for every instance we want to declare. So if we want to declare R to the... We don't have to declare R4, R5, R6. We can do R to the N, but we're going to have to do it for R to the N. We're going to have to do it for R to the N with fin. So let me... first, I need to create... I'm I'm gonna do it piecewise. Ultimately, like from a design perspective, I'm gonna be creating a vex scope. But the question is how scope interacts with type classes, and I need to do more research to figure that out. And I can do that research on stream, I think. But we're not there yet. I don't think we're going to be there until we have the type class. So this is we're just gonna deal with R to the N before we get, as we build our way through the book into the type class, and then we're kind of gonna go back because it's like chapter 1.b is where it defines vector spaces, and we're still in 1.a. We have to we do need this theorem though, so let's begin. Let's write a proof, everybody. We're finally proven. I think induction on nat, right? Yeah, it's induction on nat. Induction on n. Now, how do I prove this? Unfold addition. No, you know what? It's going to be induction on x's. It's going to be induction on x's. But... oh, no, we're going to get stuck, aren't we? That should be fine. It should be fine if we get stuck. If I try this... no, see, it doesn't work. It can't generate the goal state because it can't generate the goal state when x is so you can't do double induction. It's going to be single induction. It's going to be single induction. So y is, there's only one inhabitant of TR0, right? So since there's only one TR0, I should be able to prove that y is equal to nil r. I have to be able to show that. Inversion y doesn't do anything. Let's see here. Let me just unfold stuff and see if that gives me any ideas. It did not give me any ideas. It did not give me any ideas. All right, this is... induction x's. I can't induction y's because it won't generate the goals. I actually don't know how to do this. Wow. This shouldn't be that hard, right? This is nothing. You know what? This is because of those exercises I skipped in Solver Foundations Volume 1. That's what happened. Is I skipped some exercises. Oh, you know what? Let me make it... You know what? Here's what you have to do. You have to revert y's. And then induction on x's. And then intros y's. It's a subtle difference, but... No, that's not a difference at all. Because it already infers the 0. If I have a type with one inhabitant in the context, how do I show that the value is that inhabitant? Yep, that didn't help. Googling that did not help everybody. All right, so Matt, now would be a good time to make me do the fin thing, because vectors is not going well. But this should be easy to do with fin. Unfold addition. Oh, there you go. No, you can't do induction on y's. Because it's really not... Should be a REFL. Something like x plus 0 equals x should be a REFL. Hmm. There has to be a way to show that. Well, I don't have a proof that it would be inversion. Oh, search is great. You can you put in a type and it shows you everywhere that type shows up. Yeah, this literally searches like the everything for. I mean, it's totally not helping, but. Let me go back to induction on N. And see if I like that any better. This is how I do proofs. Like, I fail and I like. No, that doesn't help. Because for the same problem. For the same problem. I don't necessarily have a proof. I mean, print TR4. Why would that not? Does it want parentheses? Print T. Nil is the only type of TA0 for every type. Nil is the only inhabitant of TA0. Can you skip to the induction case? Yeah. Unfold, addition, simple. Simple. See, this doesn't work. Because now X is... Oh, no, that's fine. Now X's is a different X's than it was before. Like, what I can do is I can specialize IHX's at tail Y's. And I get this inductive hypothesis. And what I need to do is I need to unfold addition in IHX's. I think you need some zip width lemmas. I think I need zip width lemmas too, which I don't want to do. I don't want to go down that road, but I think I have to. Simple in IHX's. Zip width R plus tail Y's X's. Hold on. Yeah, the rewrite worked. The rewrite totally worked, which is good. it should be. Oh no, it's not, because it doesn't destruct on the zip width doesn't destruct on the first argument. So I'm gonna need some zip width lemmas. I can't even think of exactly what they are though. Cons are head plus headwise, H plus headwise, and zip width R plus, tailwise X's. I almost wish I could do it the way this proof has it. The way the proof in the book has it. If you replace add with any commutative function, yeah, add has to be with any commutative function. I mean, you know what though? There's no. That's a problem with our field class though. No, it's not a problem with our field class, because the commutativity of add is in the field theory requirement for the instance declaration. Like, you need that proof. We didn't talk about it because I stole the proof from verified quantum computing, but it's in there. So R add, which becomes R mult with this instance, is really the only thing that the compiler knows about that function is that it's commutative and that it interacts with 0 in this particular way. Just add the hypothesis FAB equals FBA. I mean, I don't think that'll help. Assert radd H headwise equals radd headwise H. It'll help us think of the lemmas that we need. Yeah, I see what you're saying. So plus is currently, I'm in R scope, so plus is currently R mult. And then there's a function, I mean, I can just do LRA. LRA is not imported. Simple in H, rewrite H. That's good. I mean, that's technically progress. Like, we are a step closer. Do you ever try to force proof space into a metric space and try to think in your head of how proofs are near each other? You know, I don't think it actually works. Someone would have done it if it worked, but that would be cool, wouldn't it? If you could actually say that a language is a metric space, a proof language is a metric space. I do not. No, I do see what you're saying. I got excited with the rewrite because I could rewrite it, but it's. Oh, you're saying. I see what you're saying. You're saying this, and we should do this in the other file, but theorem zip with com ABC type F. Well, I won't be able to prove this for arbitrary F. I wouldn't be able to prove this for arbitrary F. But let's just start it anyway. No, Garrett, you're 100% right. I have too, but apparently I haven't learned. You know what I mean? Like, yeah, blindly doing rewrites. Yeah, I know. You're 100% right. Well, you could pass it. You could make this dependent on a proof that F is commutative. You could make this dependent on a proof that F is commutative. TAN Y's TBN F A into B into C. I need a for all. And then ready? H for all A, B, FAB equals FBA. And that's the end of that. That's the end of the premises. Zip with F X's Y's equals zip with F Y's X's. Oh, no, this isn't the type signature of a commutative function. A commutative function... I think this is what we want. Proof. Intros. Generalized dependent Y's. What if... This is taking a really long time. But we have to do it. We have to slog through at a low level if we're going to figure out how to do it at a high level. Or, I don't know, maybe this isn't the way to do the stream. I'm not gonna bail on what I'm currently doing. Maybe the thing to do with the stream is to actually read a whole chapter and then go back and code it up. specialize H at H and head Y's. The reference Y's was not found in the... Oh, because I didn't intros. It's still the same problem. Alright, you know what we should do? We should... what should we do? I have to get these proofs done, but I want to move forward into the getting the type class for vector space. We still need to think of the lemmas. I know. This seems like it's on the right track, but it's actually the same exact problem. It's actually the same exact stuck state. Believe it or not. What's less distracting? Because you're not carrying around other assumptions? I still don't know what you mean. Tailwise should actually be able to it just unfolds the first one. But tailwise actually should be able to be consumed by the function. Let's look at the last const. These are all fixed points, definitions, lemmas. No, it's not the trunk lemma. And these are just definitions too. Is it eq dex vector spec? Nth order head. What is that? What is nth order? Don't understand that. Let's see. Shift in. Here, let me make this bigger. Replace const. What a nightmare. This proof is a nightmare. It just makes me not want to work with vectors. And even if this is admitted, it doesn't actually help. Well, yes, it does. It entirely helps. It's the end of the proof. When you pass a commutative function into zip with, zip with itself should be commutative, or zip with f. All right. Alrighty, here we go. We will continue. We need to make an executive decision. Do we keep fighting with this proof? Hold on. I'm not thinking. I'm not using my head. That's what's going on here. Cons on the left versus cons on the right. Inside, I'd say set a timer for 10 minutes. That's a good move. That's always a good technique, is setting a timer to think of relevant lemmas. So we're only going to think of relevant lemmas. So what do we need? Here's a relevant lemma. Lemma A B, C are types, N is a nat. F is an A into B into C. X is a T A nat, is a T A N. Y is a T B N. Y is a TBN. And what we're going to do is we're going to cons then you could use oh, that's a good lemma. That's a good lemma. I was going to define, let me finish this thought. No, this is the same thought. No, this is the same thought. And the notation you were using made it take me longer to figure out that it's the same thought that you and I are having. It's totally the same thought. I'm missing a comma. That's a problem. This is right. This is the right idea. So let me just double check that we have the same idea. Yeah, we had this. We had the exact same idea. We had the exact same idea. There's another way I could notate it that it might let me do. No. X A X is TAN Y B Y's TBN comma con CFXY N zip with F X's Y's equals zip with F cons A X and X's cons B Y and Y's. Yeah, it worked with that notation. The notation closer to what you gave me worked. So if we do intros, what do we think? Generalized dependent Y's, induction X's, intros Y's. And it's the exact same problem. I need a lemma. Here's the lemma I need. Here's the lemma I need. I need a lemma that says, oh, no, this is perfect. This is perfect. This is great. Watch this. Watch this. This is a great lemma. A is a type. For all x's of type TA0, x's equals nil A. That is what we need to prove, baby. That's what we need to prove. That's been our blocker. That has been our blocker. This is just unfold on the RHS. Are you talking about this proof? No, it's not. Because you can't unfold cons. It's not an unfold. It's not an unfold at all. Oh, wait, this is reflex. What? No, after simple, it's refle. Did I just not see that? Oh, my goodness. It's just refle. And this is not refle. There's no way this is refle. I'm going to expand this screen. Oh my god, this is REFL. You're kidding me. How can that be? I must be missing something. Oh, dude. Because it's literally the definition of zip width. No, you're 100% right. All right, so what are we calling this? What are we calling this? We're calling, I have no idea what the name for this thing is. Zip width lemma 1. It's amazing how, like, zip width step. Yeah, zip width step. I like that better. This is amazing. This is coding right here. This is programming. That's what this is. Okay. First of all, wait a minute. Where was that thing that I wanted to do? Oh, I wanted to do B. I still need to do B. And if this is provable, where at? I'm sorry, I'm jumping around. So like by the time I read your comments, I'm totally looking at something else. Oh yeah, this is going to be induction X's. No, it's not going to be induction X's. That doesn't look provable. That doesn't look provable at all. And it's not destructible. Rewrite B with X's equals to Y's. It's not bound in the expression. Oh, no. It's just this. Combinator. That should have worked. It needs to be ignore the implicits. Rewrite H and reflexivity. What are you talking about? Here? Now I'm seeing it come together. I'm almost to the point where I can use the inductive hypothesis. Yeah. Yeah, we keep going back and forth between cases and everything, and I'm jumping around between different lemmas, and you're trying to talk about one thing, and I'm looking at another thing, and it's a little tough the way I jump around. But all right, let me just look at this. Cons headwise to x's. That I don't like. I don't like rewrite h. Yeah, you know what? We blew right. No, no, no. Rewrite h has to be before zip with step. It's got to be. I'm just curious what will happen. Yeah, that's what I thought would happen. Oh, simple. But simple isn't good. No, that's not it. It's got to be simple. This should be easy now that zip with step. We need a lemma that does a little induction somewhere. And just think, this isn't even primitive recursion. Like, I read the little typer in that language pi. I mean, that was even harder than this. Okay, I'm just staring at this. Yeah, that's a pretty good technique. That's a pretty good technique, is to do it informally first. for all f, which is a into a into b, for all x's of type vector, it's actually for all x's, y's of type vector an, zip with f x's, y's equals zip with f y's, x's. Okay. Proof. So informally, I can do the base case because I know that there's only one inhabitant of nil a0. So informally, I can do the base case. End on x's. Left side equals zip with f x cons x's y's, which equals, because of my definition, it equals fx headwise cons zip with x's tailwise. Now the right side can't actually do anything. It can't actually take a step even. Zip with f y's x cons x's. And the right side can't do anything. The right side can't do anything. Well, no, we have the theorem. What theorem do we have? What does zip with step look like again? Oh, then we can apply zip with step. No, we can't even apply zip with step. You know why? Well, we can apply it to the right-hand side. doesn't that just take us back to where we were? Yeah, zip with step would just take us back to where we were. So we need something to destruct on the right, but our definition of zip width just like ignores that. What I want to be able to do is, if I have a proof that zip width is injective, zip width is injective. Theorem, zip width. It's easier to prove map uncurry plus zip x's y's equals map uncurry plus zip x's zip y's x's. Yeah. I don't see why that would be easier to prove. Come on. Ugh. Equals w's x's equals zip width f y z's implies w equals x's and w's equals y's and x's equals z's. I don't think I can prove this though. Cannot infer the implicit parameter of nat. Okay, for all w's, y's of type TA and for all X's, Z's of type TBN. I don't know if I can prove this. Inversion H? No, inversion H doesn't do anything. It should. Nothing. I always forget what the injection tactic actually does. No, this isn't true. This isn't even true. This isn't even true because if you add together numbers, it deletes information. Like you could have pairs of lists that have the same sums, but they're different. So this isn't even true. I don't know why this isn't working. The expression B of type cannot be applied. B is not a type. Oh no, there's a naming collision. There's literally a scope conflict. Empty vec has exactly one. That was a scope conflict. That was the problem. Empty vec has exactly one. This does not look provable at all. This does not look provable at all. It's an important lemma, and it's true. But if inversion X's can't do it, which it should be able to because it's an inductive... It's not inversion... No. Print T. Nil is of... For for every n, nils of type TA0. All right, so let's continue as if we proved this, and we'll come back and finish the proof later. I like map uncurry plus zip x's y's equals map uncurry. I don't like that. That's I just don't think I like it. So let me zip with step and empty vec has exactly one. Let me bring these into utils for now. I'm like not going to keep I'm not going to keep like worrying about structure and everything. It should be in the current environment. I might have to just go back up here and re-import. Yeah, I just had to re-import. So yeah, we're not doing too good. But let's see where else we get, because I want to try the vectors.fin idea. Where it's maps from. So in verified quantum computing, it's literally like this. In fact, let's read verified quantum computing. Topological quantum computing market. Matrix. Vector n. So look, a matrix is a function from nat to nat into C, right? And this is the syntax I was looking for. Bind scope vec scope is what I'm going to do. Bind scope with, okay. But like literally like, then what's nth? The vectors are simply functions from nat into the field, right? And that makes sense because it's indexing. It's indexing. And we might want to play with that, but I want finite. I want them to be finite. So that's where fin n comes in. fin n is a convenient way to represent 1 dot dot n. Fin n can be seen as an n-tuplet of unit of unit. F1 is the first element of the n. If f is the kth element of the n-1, then FSF is the... I need to understand this data structure, because this is the data structure I think I want to work with. But we're not going to be able to experiment until we have our vector space class. So let's continue reading, and I'll just take notes. Yeah, I should really switch. You can also just say that fin n is I such that I is less than n. I know, but sets are just bad news. Sets are just bad. Why is that one too? Oh, no. Like, definition fin and nat is defined as a set. I forget how set notation works, but I don't want to do it because it's terrible. I need to, since I'm in, I need to do this. But using sets as types is like not trivial. Like you need, like it needs to be like records. Oh no, that worked. But I feel like since it's homebrewed, I'd have to like make a bunch of stuff. I have to make an nth function. And why would it be into set? Oh, because it's just the value. It would be into set. So like definition nth. X is a vector. X is a vector and K is a nat. And the result is an R. I don't even know how to implement this. How to index. I mean, the point of vectors being functions from nat to R is that it's trivial. It's just trivial application to do nth. I thought the fin class, the fin type would work differently. We're experimenting. That's okay. Require import vectors.fin. So definition R4 is defined as fin4 or T4 arrow R. Oh, I'm not in local open scope R scope. Yeah, the proof I was trying to do before is much easier if I can just get this working. I know. This should work. This should be working, though. All right, let me I do not know why that's not working. It does work. It does work. Just when I imported fin, it threw off my scoping, and I'm not managing scope in a smart way yet. So like definition data of type R4 should be a fun n of type T4 into 9. So it's just a vector of all 9s. And that works. So if I say check data 5, that should fail. But nat. I would need to construct like a T scope. All right, give me a hot second. I'll be right back. Got some coffee on. All right, let's unknown scope delimiting key 3. So like what we can do is we can say definition Rn is defined as nat into R. And then we can say definition data if I want data of type R something, fun n is a nat, arrow, match n with 0 data, 1 data, and if this is just R2, then underscore 0. This is similar to how he ends up doing it in verified quantum computing. Where all entries are 0 if they're not the particular data. So it's an interesting way to think of vector spaces. I mean, think of just a set of matrices, r to the 4 times 3. Like, imagine that as like your data, which your critical data, which is your 4x3 matrix. But imagine what's really going on is it's extending infinitely in all directions with it, where it's all zeros. And matrix multiplication still works that way. Like, still holds up. You just have to orient, like, well, it's not extending all infinite zeros in all directions. It's only extending out infinite zeros, like, down and to the right. But none of this matters until I'm making an instance of my vector space type class. And my vector space type class doesn't matter until I get to that part of the book. So I'm going to do some reading now. Hi, what IDE am I using? Hello, MF Cecilia, good to see you. I'm using Emacs. Coffee's boiling. Hot coffee. And this is just one theme. It has a lot of themes I can try, but I'm enjoying this theme for today. I'm trying to do a different theme every day. All right, so let's read some of the book. Single letter is used to denote an element of Fn, and the same letter with the appropriate subscript was often used when coordinates are displayed. So I'm going to roll over to that. Instead of doing x and x's, I'm going to do x and xk, or x and x1, you know. Even better, work with just x and avoid explicit coordinates when possible. Definition 0. Let 0 denote the list of length n whose coordinates are all 0. So this is a book that does not do with the little arrow on top. The 0 with the arrow on top, unfortunately. Here we are using the symbol 0 in two different ways. On the left side of the equation 1.14, the symbol 0 denotes a list of length n, whereas on the right side, each 0 denotes a number. This potentially confusing practice actually causes no problems because the context always makes clear what is intended. Did he just say, no, potentially confusing? I thought he said intentionally confusing for a second. But yes, potentially confusing practice actually causes no problems when the context makes clear what is intended. Yeah, so x plus 0 equals x, blah, blah, blah. So that's just saying the notation. And we're going to have to play with scope and do some interesting stuff to deal with that. A picture can aid our intuition. We will draw pictures in R2 because we can sketch the space on two-dimensional surfaces such as paper and blackboards. Typical element of R2 is a point x equals x1, x2. Sometimes we think of x not as a point but as an arrow, starting at the origin and ending at x1, x2, as shown here. When we think of x as an arrow, we refer to it as a vector. When we think of vectors in R2 as arrows, we can move an arrow parallel to itself, not changing its length or direction, and still think of it as the same vector. With that viewpoint, you will often gain a better understanding by dispensing with the coordinate axes and explicit coordinates and just thinking of the vector as shown here. Whenever we use pictures in R2, we use the somewhat vague language of points in vectors. Remember that these are just aids to our understanding, not substitutes for the actual mathematics we will develop. Although we cannot draw good pictures in high-dimensional spaces, the elements of these spaces are as rigorously defined as elements in R2. Mathematical models of the economy can have thousands of variables, say x1 to x5,000, which means that we must operate in r to the 5,000. And you get that r to the 5,000 is the Cartesian product, right? It's Cartesian product of where each item in the product is like uncountable. Such a space cannot be dealt with geometrically. However, the algebraic approach works well. Thus, our subject is called linear algebra. For example, 2 minus 3, 17, pi, square root of 2 is an element of R5, and we may casually refer to it as a point of R5 or as a vector in R5 without worrying about whether the geometry of R5 has any physical meaning. Recall that we define the sum of two elements of f to the n to be the element of f to the n obtained by adding corresponding coordinates, see 1.12. As we will now see, addition has a simple geometric interpretation in the special case of R2. Suppose that we have two vectors x and y in R2. You know what? We're going to try to do an instance list. We're going to do instance list of vector space class. I think we're going to try it. Suppose that we have two vectors. Recall that has a simple geometric, it's a special case of R2. Suppose that we have two vectors x and y in R2 that we want to add. Move the vector y parallel to itself at its initial points, coincides with the endpoint of the vector x, as shown here. The sum x plus y then equals the vector whose initial point equals the initial point of x, and whose endpoint equals the endpoint of the vector y, as shown here. In the next definition, the 0 on the right side of the displayed equation below is the list 0 in f to the n. Additive inverse in f to the n. For x in f to the n, the additive inverse of x, denoted minus x, is the vector minus x in f to the n such that x plus minus x equals 0. In other words, x equals x1 dot 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 x to the n. If x equals x blah blah blah, then minus x equals minus x blah blah blah. Did we define scalar mult yet? I forget. But what we can do is we can definition I'm gonna create notations later. It's gonna be fine. Definition additive inverse x. A is a type field of A. N is a nat. And it X is a TAN. And it lands in a TAN. Map, ROP, X's. I think this is it. I didn't call it ROP, I called it additive inv. Yep, we defined additive inverse. And then we haven't mentioned our notion of 0 yet. I'm waiting till I get to the vector space type class before I introduce the notion of 0. That'll be important. I'm going to start sketching this type class right now. Class vector space. We're going to do camel case, I think. For no, it's not going to